Hi everyone, welcome back. Lecture 2. So today we will talk about prefix free codes and Crafts inequality, which we will learn about shortly. Right, so let's start with the quiz from last time, which will also function as a recap of the last lecture. Okay, so we want to design fixed length codes for an alphabet of size 9. And the first question was, what is the length in bits per symbol for such a code? Right, and in last class we saw this formula that if your alphabet is like this X, then the bits per symbol is log base 2 the size of the alphabet, the ceiling of that. So in simple words, basically you find the nearest power of 2 which is bigger than your size, right? So 9 lies between 8 and 16. So you take 16, you take like log base 2 of 16, which is 4. And so 4 is the number of bits you need if you are going to represent this in a fixed length code. Is everybody okay with that? I think most of you got this one right, so that's good. Okay, so one thing you will immediately observe is like if your alphabet has size 8, then you're spending log 8 equal to 3, right? If it's 16, you're spending log 16, which is 4. So powers of 2, this seems to be working really nicely. But for 9, you see like clearly, like you want this, right? This is what you want. This is somewhere between 3 and 4. But this is not what you got. You got 4, which just seems like suboptimal. So this question was trying to introduce you to one idea to make it better, right? So the idea is simple. Rather than encoding one symbol at a time, you encode symbols in blocks of 2, right? So if your alphabet was like A, B, C, D up to like H, I, right? So the original code, what you would do is like A becomes 0, 0, 0, 0, B becomes 0, 0, 0, 1, so on, right, up to I. Now what you will do is you will create a new code, which is like AA, AB, AC, AD, dot, 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 right, up to II. So effectively what you're doing is you're creating an alphabet of size 81, right? You're creating the product alphabet of these two. And then we asked what is the length in bits per symbol for this code, like a fixed length code applied on blocks of 2. Here there were mistakes both on our side because we made a typo in the next question and which led to some of the students getting this wrong. But I think you got the concept right. So again we use the same trick. We know that 81 is less than equal to 128 and greater than 64, right? This is 2 power 7, this is 2 power 6. So really, if you calculate this will be 7. So many of you got it correct that you need 7 bits to represent this pair, right? So AA becomes like 7 bits. So this becomes 0, 0, 0, 0, 0, 0, 0. And then so on for the other guys. However, the question we asked was bits per symbol, not bits per block. So here the bits per symbol is, each block has 2 symbols, right? So just to make it very clear, block is like AA and symbol is like A, right? So each symbol and then you have a block of 2. So the length in bits per symbol is this divided by 2, which is this divided by 2, which is 3.5. Yeah. And those who wrote 7, we will still give you marks because we made a mistake in the next part where so let me read the question. So now the alphabet size is 81 because we will be encoding pairs of symbols together. So the length in bits per, so this was the typo we made, it should be bits per block, is log 81, 7. However, we are encoding blocks of 2 symbols, so the length in bits per symbol is this divided by 2, 3.5. And did working in blocks of 2 give a better compression ratio? And I think most of you got it right. The answer is yes, right? So we went from 4 bits per base, 4 bits per symbol when we were encoding them one at a time versus like 3.5. I wanted to do this. Can someone be kind and tell me what is log 9 base 2? I just want to see how close we got to that.
It's like
Okay. Yeah, it's 9 is very close to 8, right? So we assume it's only a little bit above log 8, which is 3. So we got to 3.5. We didn't quite get to log 9. Can somebody suggest how I can get even closer to this many bits per symbol?
Create larger blocks.
Yeah, very good. The answer was larger blocks, right? Simple idea. Instead of doing 2 at a time, you do 3 at a time. So you have like 9 cubed possibilities and so on. And you can keep going, and you can show actually, if you work, just do some math, that you will actually eventually converge to 3.17. And we will see this sort of scheme and even better ideas to achieve this, because you can see that this is not particularly optimal. Like, your alphabet is just growing exponentially as you make your block bigger and bigger. So we will come back to this. For now, I guess just notice that you can do better than fixed length codes by using some clever ideas. Okay, and any questions on this first question? Okay. Second one is very simple, right? This is the sort of quiz question, like you listen in class and you solve it like in a second, basically. So, yeah, I think everybody has got this right, but let me quickly do it. So the length, so the question is, you are given a random sequence which is sampled from some probability distribution, and you encode it with this code. You want to compute the expected code length, right, which is our usual like metric for determining the goodness of a code. So the length of each code word, you can just write 1, 2, 2, right, and then you can calculate the expectation. This is just making sure you remember your probability. So PA times length of A plus PB times length of B plus PC times length of C, which is 1 plus 0.3 times 2 . Okay, 1.5, I hope I got it right. Bits per symbol, right. I find it useful to always write the unit bits per symbol, because that way you don't make mistakes like the mistake that we made in the question. Yeah. Okay, any questions on this? Okay, good. Okay, I gave an exercise in the last class to decode this. Was anybody able to decode? So this was the code we gave, and I wrote down a sort of encoded sequence, and I wanted you to get back to the original sequence. I see a couple of hands. Anybody else? Okay, let me ask you for the first, and then I will ask you for the second. So what's the first symbol, first decoded symbol? So the answer given is D. And why is it D?
Because the only code that starts with a 1 and then has another 1 and has another 1 is D.
Right, and the answer is that, like, the reason why it can only be D, right? Because you have a code word which is like 111. Like if it was A, then it must have a 0 somewhere, and if it is B, then 10, so on, right? So there is only one possibility really, and we'll come back to this later in the lecture. The next one.
Yes, the next letter would be like C, and then like we basically can just keep reading each letter until we get to like a 0.
That's a good way of thinking, right? Like so the answer was, you just keep going until you hit a 0 because of the particular way this code is structured, right? When you hit a 0, if you have like 3 ones in a row without a 0, then you know it's a D, right? If you have 2 ones and then a 0, then you know it's a C, and so on. Let me decode a couple now. So after this you have 1. So when you see a 1, you know it's either B, C, or D, right? It can't be A, so that's eliminated. And then you see a 0. So you immediately know it has to be a B, because if it was a C, then it will have a 1, 1, and D also will have a 1, 1. So it has to be a B. Sorry. And then you see a 0, and you know only one code word starts with a 0, which is an A, and so on, right? I hope you are decoding this at home, but I hope you get the gist that Even if you have a variable length code, right? This was a variable length code, and last lecture we had some concerns from students that how will you decode it? But you can see like there are variable length codes that can be decoded, and this is one example. And we'll look at it in more detail and like characterize when exactly can you decode these things. Any questions on this? Anybody who wasn't able to decode and doesn't fully understand the process right now? Okay. And we will go through like an actual algorithm for those who like to think in that way. Right. Okay, so the outline for today, no sense going through the list, like we'll get to them when we get to them. But the first item is we will define what do we mean by lossless compression in this context. And we will discuss two specific categories of codes. Okay, so I will write down a few codes and I will ask you whether they are lossless or not. Okay, is this lossless? No. I hear no. Why is it not lossless? What? Yeah, because of the ambiguity in the sense that A and B have the same encoding. So clearly, if you see a zero, like you only see zeros, so you can never tell whether A or B was transmitted, right? So this is not lossless. This is very much not lossless. Okay, now this one. Is this lossless? So is it lossless or not?
It is. Sorry,
it's not lossless. Anybody else who has a differing opinion? What do we mean by lossless, I guess, right? Like if you know you're only going to ever send like one symbol, then this is lossless, right? If you see 1 0, then it's an A. If you see 2 zeros, then it's a B, right? So in that sense, it is lossless. But very rarely do you want to send only one symbol. Most often you want to send a sequence of symbols. And in that context, if you see like A will encode to 0 0, B will also encode to 0 0. So if you receive a 0 0, you don't know whether the original person sent a AA or a B, right? So in that sense, it's not lossless. But you already start seeing that like the definition of lossless is not obvious, right? Like you need to define it carefully. Otherwise, it's not clear what do you mean when you say it's a lossless code. Yeah, so let's define it. Yeah. Okay. So we will define something called a uniquely decodable code, and it's a very simple definition. So a code is uniquely decodable if no two input sequences, say xn, ym, where m and n are greater than or equal to 1, are encoded to the same code, or I guess let's call it same output. Are we happy with the definition? Any questions on this definition? Right. So with this definition, if we go back, or let me draw that again. So like this code that we saw, A was 0, B was 0, 0 is not uniquely decodable. Before we move on, so when we talk, for example, right, we have a sequence of words, right, and sometimes you have two words such that like they are individually words, but when you join them, that's another word. That's possible in English, for example. So when you talk, right, and you talk to someone, how does the other person know when does the word end and when does the other word start? Forget about codes for a second, just like very generally. You have spaces. Very good, right. So oftentimes, like this is one way of thinking about it, right? Because the way we are thinking about it is when you have AA is encoded to 0, 0 without any gap, right? It's just 0 followed by 0. There isn't a gap. B is also 0, 0, no gaps anywhere. So that's the sort of setting where we are thinking about these uniquely decodable codes. And most often when you're working in any real application today with computers and so on, you can't afford gaps because you have a binary alphabet you're working with. You have 0 or you have 1, right? You don't have a third symbol to signify that, okay, like now one code word has ended. Now we will pause for a sec. In the old days, some of you might have heard of the Morse code. So this was used in the telegraph, which was the only mode of like intercontinental communication for a long period. And even like during my dad's time, like that was the way people sent fast messages in India. So Morse code is comprised of dots and dashes. So it's a way to like, you can represent any letter or any number in this code. And you have a dot or you have a dash. So let's look at the code and then we'll come back. You can see this, right? Yeah. So for example, E is a dot, right? S is a dot, dot, dot. Q is a dash, dash, dot, dash, right? So you just send a sequence of these. And on the other side, just listening to the dot, dash, the other person can decode it. So this was the Morse code. And how did the Morse code denote the separation? So I guess if you look at this, you will immediately see that you have E, you have A, and you have T, right? If you look at these three, so a E followed by a T is a dot followed by a dash, but an A is also a dot followed by a dash, right? So Morse code in our sense is not uniquely decodable, right? So this is not uniquely decodable in the way we think about it, but clearly it was used for communication for a long period. And why is that? Because between letters you would just put a space, like you will pause, like you will not send anything for a bit, and then you will start sending the next letter, right? And then the receiver would know how to like, I guess initially some human used to do it and then they made machines. But the idea is that in different types of communication systems, you can have different ways of doing things, right? Like for us, like this is very important. This is what we'll be working with, and this is how most modern compression algorithms work. But there are other systems also. So you should be aware. Like putting a comma after every letter in a way. Okay. Anything interesting somebody observes, like anything that we saw in the last class and you see reflected here? Like look at the lengths of the different code words. Anybody wants to like, what do you see here? Anything interesting with the letters and which letters are getting shorter codes and which letters are getting longer codes? Good. Yeah, so the vowels are shorter. That's one suggestion, and that's true. E is a single dot, I is a dot dot. Some of the vowels are a bit longer, like U is a dot dot dash, right? But you see T is very short, right? And if you study like the frequency of letters in English, you will see that E and T are the two most commonly used letters, right? So the vowels are shorter because they are also usually very commonly used. So even in the Morse code in those old days, they knew that for more frequently used letters, you should use a shorter symbol so that your overall message becomes shorter, right? So that's just, I think, an interesting fact. Any questions with this?
Could you go back to the previous slide?
This one? Yeah.
And the previous one.
Yeah.
Yeah, so the X and then Y and
So they are just two input sequences, right? So if we were to give an example, right here, if you take x2, so which is like two tuple sort of x1 comma x2, which is like a comma a, or you take y1, which is just a single input, which is b, then you can see that the encoding of x2 is the same as the encoding of y1, which is 0 0. Yeah, so that's what we meant. Sorry if the notation is new. I think I will define it more properly in the next part, or you will also get used to it. But yeah, that's just a tuple x2 or xn. So we are saying that it's not like n and m don't need to be the same, right? Any two sequences with different lengths, they should never map to the same output. Right? It should be unique. Like given the output, you are not only able to decode, you also know how many input symbols were there. So it's a very strict property in that. Is that clear? Okay. Yeah. So we will not talk about uniquely decodable codes for the rest of the class. You will see a question in the homework, and I will explain later why we don't talk about these. It's a very powerful property, but you don't really need this very powerful property. We'll see a much smaller class of codes, which is very, very easy to deal with, and we'll just stick to those. So that's our next topic. Yeah, but there will be a homework question where you will look at these and do some proofs with these. Okay. Let me find the old code we had. Yeah. So this is a proposed decoding algorithm for this code. Let me talk through this in words. So you start with an empty, you have a variable called C, which is like storing your sort of code, like the encoding. You start with empty. You look at the next bit, you add it to C. You check if C is in the table, right? So if C is in one of these 4 entries. If C is there, you decode. And then you set C again to like empty. And if C is not in the table, you just continue and then look for the next bit and you keep adding the bit. Right? So a very simple algorithm, linear time and so on. I will do an example, but before that, anybody Do people like generally understand the idea behind the thing? Okay, let me do an example. I think that should help. Yeah. And yeah, as Pulkit said, like, apologies if you have done information theory and all this, I think, probably this lecture and the next lecture will be mostly recap for the info theory experts, but after that you will see a lot of new material. Okay, so let's do an example for the same code. So we have, let's say, 0, 1, 1, 0, 0, 0, something. Okay. So we do it step by step, right? First step, C is equal to 0. Sorry, first step, C is nothing. So null, okay. Then C is 0. You decode A, right? Because you immediately see that 0 is in this table here. So you decode. So this is your code word you're trying to decode. Then C again becomes empty. Then you put C equal to 1. You can't decode here. There is no code word which is 1. Then you see C is 1, 1. Again, there is no code word which is 1, 1. Then you see C is 1, 1, 0. And here you can decode C. Okay, can somebody help me with the next few steps? What happens next in this? So after I decode C, what is the value of my variable C? Yeah, C becomes empty again. Right after you decode, you reset C. Okay, next step. So we are here basically. Next symbol is this one. Yeah, so next step you insert 0 in C, right? Are we ready to decode? Yeah, why are we ready to decode? Because 0 is one of the code words, right? 0 is the encoding of A, so you immediately decode A. And so on. Let's not do it too much. Okay. So let's think about this. First of all, any confusion with this? Are we happy with the decoding? Right. Why do we think this works? What is the property of the code that makes this possible?
Basically, like, no code is like the prefix like at the beginning of any other code.
Yeah, so the answer given by a student, which is the correct answer, is that no code word is a prefix of another code word. So you see, 0 is not a prefix of any of these. So as soon as you see a 0, you immediately know that it has to be A, because there is no other code word that starts with a 0. Right? B, 1, 0. 1, 0 is not a prefix of any of the other guys. So as soon as you see a 1, 0, you know it has to be a B. It can't be C, it can't be D, it can't be A. And so on for the other ones. So let me define it. So there are a few different names for some historical reasons, I assume. So they are called prefix codes. They are called prefix free codes. They are also called instantaneous codes. Okay, figure it out. Instantaneous codes, right? So no code word is a prefix of another code word. Right, stop me if you don't follow. Why are they called instantaneous? We just saw that property, right? As we were trying to decode, as soon as we saw the symbol, we were able to decode it like instantly, right? We saw 0, we decoded A. We saw 1, 1, 0, we decoded C. You don't need to look ahead, right? You can do it in a more streaming way. As your as your bits are coming in, you are immediately able to decode. That's why it's called instantaneous code. why is it called prefix-free code? Just the definition, and yeah. Why is it called prefix codes? I think just people didn't want to write prefix-free all the time. Okay, so just a simple property. Prefix-free codes are uniquely decodable, right? So the property we saw earlier, right? The uniquely decodable property that no two sequences map to the same code. Prefix-free codes satisfy that condition. Can somebody intuitively describe why? We won't do a formal proof of this, but just intuitively, can somebody suggest like why are prefix-free codes uniquely decodable? Why are they lossless?
When you go through the algorithm and you find C in the table, you are 100% guaranteed that it's not just a part of another code word. It's that it is going to be exactly C, or exactly whatever you find.
Yeah, very good. Yeah, so the answer was, as you are doing the decoding, right, and you decode 110 to C, you know it has to be C. There is no other option really, right? So in a way, the decoding algorithm proves that it's decodable uniquely, right? There is that decoding algorithm, and if you have done math, you will want to be more formal, and we will leave you to read the textbook if you want like very formal proofs. But it's intuitively correct, and you just like write that in math and you get the actual proof. But they are uniquely decodable because there is a decoding algorithm which there is no confusion. Like you start from the beginning and you can just decode the sequence. There are no options really. Do we think the opposite is also true? Let me not dwell on that too much, but it is not. So uniquely decodable does not imply it is prefix free. So there are uniquely decodable codes which are not prefix free. And you will see examples in homework. But again, we will see that prefix-free codes are good enough for anything we want to do, really. So we will not study uniquely decodable. Like we will not study codes that are uniquely decodable but not prefix-free. That's a category we will just not worry about too much. Okay. Any questions about this? We'll talk about the prefix codes throughout the lecture. Hopefully by the end of it you will feel very comfortable with them. Okay, so second topic in the outline. So we saw one algorithm to decode prefix-free codes already somewhere here, right? You start with something and then you keep adding bits until you find something, right? This is one algorithm. We will see another algorithm. How many of you have done like a algorithms class or data structures, seen trees? Okay, nice. A few of you have seen trees. Okay, even if you have not, you will see trees now, so you will learn something. Okay. So let's again make our favorite code. Okay. So what we will do is we will map code words to leaves of a binary tree. So you start with a root, right? Every binary tree has a root, right? And a binary tree will any node in the tree will be either a leaf or it will have two children. So the root here has two children. One is the left child, which we'll call 0, and the right child is 1. And A is the leaf here. Okay. Let me draw it and then we will discuss. Very simple stuff really, if you think about it. right? So the path from the root to the leaf gives you the code word basically, right? So if we write it down, so path from root to leaf equal to code word. Any questions? This is just a representation, and we will briefly talk about like why this is interesting, and then we will use it in a bunch of proofs. Right. Okay. So let me just describe you another method of decoding that will use this tree. Okay. So the algorithm is simple, and I think you will implement, maybe, yeah. We will see the code for this next lecture as well. Okay. So you first see a 0. So what you do is you start at the root, you follow the 0 branch, right? If you reach a leaf, you immediately decode, okay, A. And then you go back to the root. So you reset, right? That's the reset step in a way. Now you're at the root again. You see a 1, you go here. You see another 1, you go again. You see a 0, you come here. You see, oh, I've hit a leaf, right? So I have a leaf, so I decode C, right? And then I again go back to the root from here. Then I see a 1, I go here. I see a 0, I go here. I hit a leaf, I am at B, I decode B. Right? Are we happy? Should I explain again? Okay. Okay. We'll keep moving, and I hope you get some practice in homeworks. You will see this several times. Okay. Okay. So now a question for everybody. Please help me. I have this other code. Please help me make a tree out of this code. And I will make the root for you, and I will put the A here. Right. But can you help me with the B and the C? Anybody?
There should be a 1.
Okay. So the suggestion is to make the 1 branch, definitely, because B and C both start with the 1. Makes sense. Okay.
Then create a 0 branch.
Yep. We make a 0 branch. Yep.
Then we write B.
I write a B. Yep.
Create a 0 branch anyways.
Does this look different from the other one in some way? Forget about the fact that some of the nodes don't have 2 children. That's fine, I think. Are there any other ways in which this differs from the previous one? Yes.
Yeah, essentially here's like C, it's a child of B. Like it's and it's meant, like in the other one, once you got to a letter, there's no children that come after it.
Yeah. So the answer is basically that here C is a child of B, right? So B is not really a leaf, right? So B is not a leaf, and the reason is that B is a prefix of C, right? So B is prefix of C. You see 10 is a prefix of 100. So since B is a prefix of C, it's not a leaf. This is not a prefix free code. It's not a prefix. So basically, so this is a property which again will not prove but very intuitive, is that prefix code is like equivalent to binary tree where all code words are leaves. And this is very obvious once you like think about it for a minute, because see, if your code word is not a leaf, if it's an internal node in the tree, that means you can extend it further and get another code word. But that means that one of the code words is a child, like a prefix of the other, right? Here, like if B was a leaf, everything would have been good. But B is not a leaf. C is a child of B. So that means the code word for B is a prefix for the code word of C, because of the way we define things here. Is that clear? Right. So you see there is an equivalence. Basically, any prefix code is equivalent to a binary tree where you have a certain property. Right. Okay. Okay, we'll move on to the next part unless there are questions. Okay, let's talk about good prefix-free codes, right? So we now understand uniquely decodable codes, we understand prefix-free codes, we know that prefix-free codes can be represented as trees where each of the leaves represents a code word. And I hinted to you, but not quite proved, that we will not worry about uniquely decodable codes because prefix-free codes are good enough for our purposes. Okay. So with that context, let's start about what do we mean by a good prefix-free code. So if you want to get like very formal with some, we'll do the proofs very systematically in class, but just some of the other stuff where you think we are not very rigorous. The suggested book is Cover and Thomas, Information Theory, chapter 5. So that's where, if you want to like read this in more detail, and also a bunch of very good questions in the, Cover was a professor here. Okay, so the first property is for symbols S1, S2, if probability of S1 is greater than probability of S2, then the length of the code word L, S1, should be what? More than or greater or smaller than the length for S2? Smaller, right? Yeah, we saw this in last class, also very intuitive from the definition of good. Good just means that we want to, actually I should have defined, let me define good, sorry, in the last slide, 1 second. Good means minimize expectation of length of the code word subject to being a prefix code. Right, that's like the optimization definition of good. Okay, I will give a second if you. We will post these notes as well in case you want to take a look later. But if you want to take your own notes because you don't like my handwriting or you think it helps you learn better, please go ahead. Okay. If I had a code where L length of S1 was greater than length of S2, can I create another code which is just, I know which is strictly better than my code, right? So the question is, this is, if I have LS1 greater than LS2, what I can do is, I can swap code words for S1 and S2 and minimize the expected loss, expected code length. Right, so if you gave me a bad code which has like the lengths in the opposite order of the probability, I could just swap them around until like increasing probability means decreasing code length, and I will just strictly get a better expected length. So we basically proved this property with this one line of argument. Okay, and let's talk about the second property. Good. Okay. Okay, so on the second property, I will ask you to trust us for now. We will prove it in the next lecture, but it's very useful to know this property to actually learn some of the. We will actually see an actual code today, a good prefix code shortly after this. The property is that the length of a symbol x should be roughly log base 2 1 over the probability of x. Right, so this is in a way stronger than the previous one, right? Previous one was a more qualitative sort of thing where if probability is higher, then length should be smaller. This is just saying that if your probability is p, then your length should be log base 2 1 over p. This is like the negative log likelihood term you might have seen in other places. Let's do an example. Uniform distribution, the simplest distribution. Okay, so let's say you just have A and B with half of probability. Then log base 2 1 over half is log of 2, which is 1. So what we are saying, a good code for this distribution where A and B have probability half each will have length of the code word being 1 for both A and B. So like A going to 0, B going to 1, that's a good code word under this criteria. Okay, let me keep going, give you another example. So let's do in general. If x is uniformly distributed in 1 to k, then a good code will have length of a symbol x equal to log base 2 k, roughly equal. Can somebody suggest when this can be like an exact equality? When can you have length? Yeah. So the answer is when k is a power of 2, you can exactly get log k. And we already saw this, right? This is nothing new. We saw the fixed length code in the previous class. We saw it again in this class. So that's nothing new, right? So this is just the fixed length code that we know and love. Right. But in general, like the best you can do is with fixed length code is Lx equal to the ceiling of log k. You can't quite do like, because it might not be an integer, the log, right? So already like you see some justification for this property, right? For our fixed length code, you can actually achieve it. And you also see that for the uniform distribution, it's a good code, right? In general, it need not be a good code, but for the uniform distribution, which also intuitively makes sense where like, since all of the symbols have the same probability, you want them to have the same length, the code word length, and the code word length must be this thing. Okay. Please raise hand, any questions? Let's do another example. Let's look at our favorite code that we have been looking at for a bit. The 0, 1, 0, 1, 1, 0, 1, 1, 1. You will notice that we don't have a length, we don't have a probability distribution for this at the moment. Let me define a probability distribution. 1/2, 1/4, 1/8, 1/8. Let me also create the log of 1 over px. So which will be 1, 2, 3, 3. So as you might notice, for this particular code and for this particular distribution, the length of the code word exactly matches the log 1 by probability. Right, 0, the length here is 1, the log is 1. The length for the C and D is 3, the log is 3. So, and this we will actually see, not today but tomorrow, Wednesday, that this code is the optimal code for this probability distribution. We are getting closer and closer to like making very powerful statements about codes in general, and which we'll use throughout the course. Right. Okay. For now, I think that's it I'm going to say. Just remember there are two properties where really the second property, first property. So focus on the second probability, that property that the length of your code word should be roughly equal to the log of 1 over the probability. Any questions on this? Because after this we are going to see a code construction that will actually achieve this. Okay, people say happy. Good. Okay, so we will now see Shannon code. I don't know if, I think Pulkit mentioned Shannon in the last, like the intro lecture. So Claude Shannon, he did a lot of great things. Among them, he basically invented the field of information theory, which has two big parts. One is compression, which we'll learn in this class, and the other is error correction coding, which is also very, very important, used in every communication you do. So this is like one of the cases where Shannon himself created this particular code, which is a good prefix-free code according to the definition, the properties we saw. Okay. I guess I won't say it right now, but maybe like as we go through the first half of the course, if you get your hands on the 1948 paper by Shannon, which is called A Mathematical Theory of Communication, read the first part, the part that covers compression. It's very interesting, written in very simple words, not very fancy math stuff. Very, very simple words, very intuitive. Yeah, you might find it interesting. Okay, so Shannon code. So this will be a prefix code, and for symbol X, we will actually achieve the length of the code word will be log base 2 1 over probability of X. You might have been seeing this log base 2 last lecture, also this lecture as well. Does anybody know why we see this 2 all that? Why not log base 3 or natural log or log base 10 or something like that?
It's because we're only dealing with like binary, just once. It's showing 2 bits. So.
Yeah. So the answer is we are dealing with binary because our output is binary. We are encoding everything into bits, right? In another world, if we had semiconductors that are like 3 levels or something, you could be working with log base 3. Yeah. So you see, it's a prefix code, and for any symbol X, it will achieve log 1 over p of X. So it's very good code in that regard. Okay. Okay, let's do the construction. Step 1, you compute the Lx, which is this function we just saw, the log 1 over px. In this class, if you see a log and like somewhere we forget to put the 2, just assume it's log base 2, unless like otherwise stated. For each x, okay, you compute it. Sort in sort symbols in sort of Lx1 greater than equal to Lx2 ... right, increasing order of the lengths. For each symbol x, so in the above order that we just sorted them in. It's a very, very simple, if you have done algorithms, this is a greedy algorithm. Assign leaf of the, like a prefix code is a tree, as you already saw. So you are just going to assign a tree at depth Lx without violating prefix condition. And this I think you will actually implement in the first homework. Very simple idea. What you do is you know that you know that your lengths have to be this log 1 by px thing, right? So you already compute the lengths. You sort the symbols in the order of their increasing length. Then for each symbol, let's say I say a symbol which has length 1. So in the tree, which leaves of length 1 are available without violating the prefix, and we'll see an example. You assign that greedily. You don't need to think too much. Next symbol, you see, okay, maybe length 3. You find a place in the tree which has length depth 3, which is not like already a child of something else, and you assign it, and you go on, and then you have a code which will work out. Let's do an example, and then if anybody has questions, we will go through the questions. I think the example will help. So A, B, C. We'll take a slightly bigger example so that it's easier. So this is x, the symbol. Px is the probability of the symbol. And let's compute L of x, which I computed at home to save us time. So 2, 2, 3, 3, 5. Okay. And then as we work through it, we will assign these code words. But when we start, we don't have anything to go with. Okay. Okay, so I have nothing initially, right? They're already sorted in the increasing length, so that's also done. So step 1 is already done. Step 2 is done. Now the first symbol you see is A. Can you suggest any code word of length 2 that I can assign without violating the prefix property? Yeah, so one answer is 0, 0. I could have done 1, 1, 1, 0, all 4. Like right now there is no code, so there is no prefix property. So just anything is fine. So let's assign 0, 0. Keep things simple. Okay. So I've assigned 0, 0 to A at this point. Okay, now for B. B I need to assign again a length 2 code word without violating the prefix property. Suggestions? 0, 1. Okay. I like it. I like people are like not straying off the code that I made at home. Okay. Okay, for C, I need a length 3. What about 0, 0, 0? Is that good? Right, 0, 0, 0 is not good. It's a child of A, so it will violate the prefix property. So let me assign something. I need to go to this branch, I think. Let's just take this path, 1, 1, 1. Okay. Right. When you actually implement it, what you would want to do is not to take like any random node. What you would want is like sort of go lexicographically, just makes everything easier, makes your algorithm more deterministic. But for illustration purpose, you can choose anything, it's fine. So I assigned 1, 1, 1 to C. Now to D, any suggestions for D? 1, 1, 0. But let me not do that. Let me do 1, 0, 1. Okay. So 1, 0, 1 I will do D, right? Just to show that it doesn't really matter. There are a bunch of possibilities here. Okay, last one, E. E, you need a length 5 code word. Right, okay. So let me do it. Let me take a path from here, and then here, and then here. Okay, so we got a prefix-free code. It satisfies this length condition. Everything is good. Question. Is this a good code? Do you think it's the best code I can make for this distribution? Okay, let's do a vote. How many of you think this is like the absolute best code for this distribution? You cannot beat it in any way in terms of the expected code length. How many of you think it is not the absolute best code? Okay, so I see a bunch of raised hands for not the absolute best. One of you, I guess, why do you think it's not the absolute best code for this distribution?
E could be significantly smaller than that.
Yeah. So the answer is E could be smaller, right? Like what's happening here? This is not something we like. Like you have E here. You could have placed E here without, sorry. I don't know how to undo. Let me, right, yeah. So you could have made E much smaller without affecting the prefix free property, right? And hence you could have improved. Even C. C is not very good, right? C you could have placed here. Right. So we said that Shannon codes are good codes. So they are good in a sense that we will define in the next, they come very close to the optimal, but they are not necessarily optimal. Next Monday we will learn about the code which is optimal. And but for now, I guess we will live with what we have got, and this is the code. Okay, so now show that this construction. So if you read this construction carefully, what you will observe is step 1 is obvious, there is nothing there. Step 2 is obvious, you can always sort things. Step 3 depends on the fact that like when you're trying to assign a leaf, there should be a leaf available. If there is no leaf available, then you can't assign anything, right? So actually, if you have done like greedy algorithms, like if you have done like the minimum spanning tree or something, you always need to prove that the next greedy step is indeed possible, right? So really the thing to prove here, which we will prove now, it's like an inductive proof. So we need to prove that this construction always works. So we need to prove a leaf at Lx depth is always available always available without violating like the prefix condition. Okay, so let me go through the proof and stop me if you have questions. If you have not done proofs before, don't worry too much, like only very small part of the course hinges on this. I hope you find the proof intuitive. It's not like one of those proofs where suddenly you get the result and you have no idea what happened. It's very like obvious in some ways. Okay, so proof. So if we like take all the things, we take this sum. This sum is 2 power. We know that the length is log base 2 1 over p of x. If you have forgotten the properties of logs, now is a good time to refresh. Now you know that the ceiling of something is bigger than the original. Like ceiling of x is bigger than or equal to x. So minus ceiling of x will be smaller than equal to x. So after like 2 steps basically, you can convert this to, you can remove the ceiling function which just causes problems. And then just properties of logs, right? 2 power minus log 1 over p of x is just, this whole thing is just p of x. So this is summation p of x, and this I think all of you know. What is the sum of probabilities? 1. Yes, I'm saying ones. Okay, 1, right? So let me note this down as 0.1. 2 power minus lx less than equal to 1, right? This is 1. Okay. Okay. Let's keep going. Okay, so say we assigned, so this is an inductive proof. So you say that you have already done m steps and now you will prove that the m plus 1th step is possible. So we assigned x1 to xm. So next is xm plus 1. So then we already saw above that the sum of all the probabilities is less than equal to 1. So therefore, if you add from 1 to m and then you add the next one, this is clearly smaller than the total sum. So this will be less than 1. Right. So this is like based on 1. Right, because this is a partial sum. This is only part of the total sum. This one was over all symbols in your alphabet. We are now just restricting to first m plus 1 symbols. Or, so what I will do now is the sort of the key is I will multiply both sides by 2 power lxm plus 1 and then I will move one of the terms to the right to get minus 1. Okay. Until now it's just multiplying things, moving around things, no special logic until now. So let me move this to the next page and then we will like look at some actual like logic. One second. Okay. So I will copy over the last point again. So I equal to 1 to m 2 power lxm plus 1 minus lxi less than equal to 2 power lxm plus 1 minus 1. Okay. Let's call it 2. Now, this is the part where like a visual representation is much easier to interpret, right? So let's look at this. If you have a tree and you are at depth, let's say you are at depth Li. You have a node at depth Li and you have a subtree below this with total depth Lm plus 1. Okay. So, first simple question. How many nodes do I have at depth L for a binary tree? 2 to the L, right? So in a binary tree at depth L, I have 2 to the L nodes. Okay. Now, if I have this node at Li and then I create a subtree, right? A tree below that node with overall depth Lm plus 1, how many nodes do I have here? How many nodes do I have here? Like, how many nodes of depth Lm plus 1 are children of a node or descendants of a node at depth Li? Yes, so let me write that down. So number of leaves at Lm plus 1 that are descendants of depth Li node are 2 to the L m plus 1 minus Li. Okay. Now let's come back to this inequality. What is it saying really, right? Each of these terms, what is it saying? So this term this is number of descendants of the code word of xi, basically, that leaf at depth lxm plus 1. What is this term? This term is the total number of leaves at lxm plus 1. So what we are saying is, if you take all the nodes you have already added, like all the leaves you have already added, you extend each of them to depth lx plus m plus 1, you see that there is still at least one node left. And let me draw it for you. But so what we are saying, and please think about this at home as well, is so what we did was, so you assigned x1 here, you assigned x2 here, x3 here, maybe you assigned x4 here, right? You are now at x5. x5 it has a certain depth, so this is like your lx5, right? Now we are saying, let's take each of these guys, extend them to the level, right? Like this. So all of these areas are like invalid. Why? Because any node here will be a descendant of the x1 node. So x1 will be a prefix if you try to assign it here. That's not good. Similarly, any node in this area is bad, right? So for example, if x1 was 0, 0, these nodes will be like 0, 0, 1, 1, 0, 0, 0, 0, all of these guys. So these are just not allowed. These are not allowed. These are not allowed. These are not allowed. So what we are trying is, we are trying to eliminate all the nodes that are disallowed by the prefix free property. And what we are showing is that even after you remove every node that is illegal, like which is not allowed, you are still left with one node which is still valid. Right? Any questions on this? I will give you time to digest, I guess. This is also written up in the notes which are available on the website. Okay, yeah. So just to finish off the proof. Right. So if we just write it like this, this is the total number of leaves at lxm plus 1 depth minus summation 1 to m So this is the number of leaves not allowed because they are descended from existing code word. So what we have basically shown is that this is greater than equal to 1. So there is at least one leaf left at every step, which you can assign to your next symbol, to xm plus 1. So at depth lxm plus 1, there is at least one leaf which is left. So that is basically the proof. Yeah. So sorry if it was too much, but I guess you have to say it. In next class we'll see another proof which is very similar, so I think that will help. Yeah. And we'll put these up. Right. I think I will not have time to cover the last topic, Kraft's inequality, which we'll do next lecture. I will leave it here and answer any questions. Otherwise, thank you. Don't be scared of the proofs if you are scared, because they're only for 2 lectures. Then it's mostly algorithmic. And about it, make examples. I think that will really help. Just make some trees and see what these quantities are at various steps. Right. Thank you.